As it does this, the amount of power being transferred across the line is increased once again until it reaches 1,500 megawatts. Once again, we are satisfying the power equation. Although the reactance of the line has increased, the phase angle has also increased to about 48 degrees. So at this point we should have equilibrium. But it's not so easy, as we have to contend with the spinning energy of the heavy rotor. The acceleration does not suddenly cease at this point. In fact, the rotor overshoots and continues advancing in phase, so further increasing the amount of power being transferred across the line. However, now we have the situation where the generator output is greater than the mechanical input. So the rotor starts to decelerate and fall back to the equilibrium point. After a few oscillations, the rotor will settle again at equilibrium. If we examine the diagram carefully, we find that this overshoot area above the line is of the same dimension as this area below the line. This lower area represents the energy stored in the rotor which provides the accelerating force. Conversely, this area above the line represents the energy removed from the rotor as it overshoots, and so provides the decelerating force. As long as these areas are equal, the system will remain stable and ride through the disturbance, in this case the loss of one transmission line. During the dynamic period, the system has quickly settled into a new steady state, with the generator advancing in angle in order to continue to transfer 1,500 megawatts along the two transmission lines. Now let's look at another example on the same section of the power system. This time the load transfer has been increased from 1,500 megawatts to 1,800 megawatts. Now let's return to our load transfer curves. We can see that with 3 lines in service, the phase angle difference must be increased to about 37 degrees in order to transfer 1,800 megawatts. Once again, consider the case where a system disturbance causes one of the lines to trip. As before, the instantaneous response is for the amount of power transfer to reduce and the rotor to accelerate from this point to the equilibrium condition again, which is now about 65 degrees. As before, the rotor continues accelerating and overshoots and continues to increase the phase angle beyond 90 degrees. At this point, about 115 degrees, the load transfer is once again 1,800 megawatts. But look, this deceleration area above the line is less than the acceleration area below the line. So the rotor goes right on advancing and increasing the phase angle. The power transfer has decreased, but the turbine is still inputting 1,800 megawatts of energy, so the rotor continues to accelerate. Thus, the phase angle continues to increase, and the generator will fall out of synchronism with the rest of the system. We'll be looking at this condition in more detail later on in this tape. From these two examples, you can see that the stability of the system is very much influenced by the initial operating condition. That is, before the disturbance occurred. Okay, let's move along to look at yet another example on the same section of power system. With 3 lines in service, the power transfer is 1,500 megawatts, and from the curve we can see that the power angle is about 30 degrees. This is the load condition that we discussed in our first example. Now let's see what happens when a phase-to-phase fault occurs on one of the transmission lines. In this study, we are concerned with what happens in the very short time frame before the protection relays trip out the faulty line. As we know, a phase-to-phase fault will cause the voltage to fall to a very low level at the location of the fault. This will cause voltages in the vicinity of the fault to fall. Now remember the power angle equation, V1 times V2 times the sine of the power angle divided by reactance XL. If the level of voltage falls, then the capability for load transfer is also reduced for each specific angle. So we can draw yet a third load transfer curve for the phase-to-phase fault condition. Clearly, with these low voltages for any specific angle, the amount of power that can be transferred is now greatly reduced. We now have to consider three power angle curves. They are: 1, the initial condition with 3 lines in service; 2, the condition with the phase-to-phase fault on; and 3, the condition with only 2 lines in service after the faulty line has tripped. At the moment the fault occurs, the power output falls drastically to this point on the fault curve. At this point, the generator output is far lower than the turbine input, so that there is a large amount of accelerating force available. As long as the fault remains on, this particular curve indicates the condition. As the rotor accelerates and its angle advances, the power input increases along this curve until at this point, say 45 degrees, the faulty line is tripped out of service by its protective relays. Conditions are now indicated by this 2-transmission line curve. The rotor now continues to accelerate along this curve through the equilibrium point and overshoots and starts to decelerate as the generator output is greater than the turbine input. The rotor angle will continue advancing until this decelerating area above the line is equal to the accelerating area below the line. At this point, power output will fall back and after a few oscillations will settle to its new equilibrium position, that is, with a transfer angle of about 50 degrees. This is an interesting case. We can see that the rotor has advanced beyond the 90-degree phase angle. Nevertheless, it's been able to recover and remain in step with the system. Now let's see what would occur if the fault were a 3-phase fault instead of phase-to-phase. With a solid 3-phase fault, the voltage falls close to zero, and the immediate consequence is for the power transfer to fall close to zero also. As before, the rotor angle advances until the faulty line is tripped at this point, so that load transfer conditions are now indicated by this 2-line curve. Clearly, this accelerating area is greater than before, and as a result, the rotor will advance to a much greater angle. Once again, we must carefully measure and compare these two areas. They appear to be equal. The limiting factor is this point here. As long as this decelerating area above the line is equal to or greater than the accelerating area below, then stability will be restored. However, this condition is extremely vulnerable. For example, if the protection relays operated slower than intended, then the accelerating area would be greater and the rotor would advance beyond this point and fall out of step with the rest of the system. It is clear that a 3-phase fault is more severe and more likely to cause instability than the phase-to-phase fault. It is also apparent that the time settings of all relays are most critical in helping to avoid instability. In these examples, we have been looking at stability behavior on a fairly simple system. Obviously, in practice, it is much more complex. In response to a fault, several generators may be accelerating or decelerating at the same time, and load transfer may be affected on other transmission lines throughout the system. Detailed system stability studies are normally carried out by the utilities engineering department in order to predict the consequences of different types and locations of faults. These studies play an important part in power system design and operation. Obviously, protection schemes are a vital part of system stability.